Hello everyone, today in this video we are going to talk about electric field due to a hollow spherical cell. After this video you should be able to derive the expression for electric field inside the sphere, on the surface of the sphere and outside the sphere. So in order to derive the formula, we take a sphere of radius capital R and charge plus q. So this is a hollow sphere, it is like a football which is charged. So there is nothing inside, but there is only a layer which is making a sphere. So this is a hollow sphere and there is a charge on the surface, and O is the center of the sphere and Q is the charge. And we know from positive charge the electric field will go away like this. So it will go away from the charge radially, that means going through the radius. So first we will find the electric field outside the sphere. So we already know this is the sphere of radius R and charge Q. So now this is the sphere of radius R and charge small q, and outside the sphere we are taking a Gaussian surface of radius small r, and the Gaussian surface is nothing but an imaginary sphere enclosing some charge. And in this figure the center of Gaussian surface and center of our sphere is same, and on the surface of the Gaussian surface we consider small area ds, and if you consider this point, the electric field due to this positive charge will be away like this, and direction of area vector, that is perpendicular to this small ds, will also be in the same direction of electric field. So I can say both the electric field and the area vector is radially outward. So theta is 0 degree out here. Electric field is EO, that means electric field outside the sphere. So now I can say on the surface of the Gaussian surface the direction of ds and E naught is same. So the flux through this small area will be given by flux is equal to closed integration of E ds cos 0 degree, and cos 0 is 1. So if you take E naught common, this is not epsilon naught, this is E naught, electric field outside the sphere, and this is integration of ds. Now I have to find the integration of ds. So integration of ds means I have to add all this small area throughout the sphere. So if you add all the area, then you will get the total surface area of the sphere. So out here I have already written integration of ds is surface area of the Gaussian surface, that is the sphere, that is 4 pi r square. So flux is equal to E naught 4 pi r square, but according to Gauss law flux is equal to q by epsilon naught. So now flux is q by epsilon naught, and we have found out flux through the sphere is this much. So I can compare these two equations and I can write q by epsilon naught is equal to E naught 4 pi r square. So if you solve this, you will get E naught is equal to 1 by 4 pi epsilon naught q by r square, and E naught is equal to, so 1 by 4 pi epsilon naught is k. So E naught is equal to k q by r square. So this is the electric field outside the sphere. So this is similar to the electric field due to a point charge. So a charged sphere will produce the electric field as produced by the point charge. Now the second case is electric field on the surface of the sphere. Now we have to find the electric field on the surface of the sphere. So for that I will take the Gaussian surface just outside the sphere so that their radius will be equal. So you can see this is our charged sphere, and just outside this dotted lines are Gaussian surface. So radius of the sphere and the Gaussian surface is same, that is capital R. And suppose ES is the electric field on the surface. ES means electric field on the surface of the sphere. So again, if you take a small area on the Gaussian surface, then the electric field due to the positive charge will be away like this, and the direction of area vector will also be in the same direction. So theta is equal to 0. So I have written the same thing. So flux through this small area ds will be given by flux is equal to es dot ds. So for dot product I can write cos theta, and theta is 0 degree, and I can take this es out because it's a constant. So es integration of ds is the flux through this surface. Now I have to find the flux through whole surface. So for that I have to do the integration. When I integrate this ds, I will get the area of sphere. This we have already discussed in our previous case. So I can directly write integration of ds is equal to surface area of Gaussian surface, which is 4 pi r square. Flux is es integration of ds, which is flux is equal to es 4 pi r square. So according to Gauss law, flux is charge enclosed by epsilon naught, and charge enclosed is the charge of the sphere, which is q by epsilon naught. So now comparing this and this equation, I can write q by epsilon naught is equal to es 4 pi r square. So when you solve this, you will get es is equal to 1 by 4 pi q by r square. So this is the electric field on the surface of the sphere, and the only difference from the electric field outside the sphere is this r. So for outside the sphere the distance was small r. Now on the surface the distance is capital R. Now third case, electric field inside the sphere. So for that I take the Gaussian surface inside the sphere. So this is our charged sphere with charge q, and our Gaussian surface is inside the charged sphere, and the radius of Gaussian surface is small r. So similarly I'll take a small area ds on the surface of the Gaussian surface, and out here I'm considering electric field, and the area vector is in same direction. So theta is equal to 0. So flux through the Gaussian surface will be given by phi is equal to close integration of E dot ds, and flux is equal to E ds cos theta, and similarly I can write flux is equal to E, I means electric field inside the sphere, integration of ds. So when I integrate the ds, I'll get the surface area of the sphere, so that is 4 pi r square. So flux through the sphere is ei 4 pi r square. Now according to Gauss law, flux is charge enclosed by epsilon naught, and phi is equal to charge enclosed by epsilon naught. If you see the Gaussian surface is inside the sphere, charged sphere. That means inside this Gaussian surface there is no charge, because charge is on the surface of the sphere, but our Gaussian surface is inside the sphere. That means there is no charge inside this sphere, so charge enclosed will be 0. So out here I have written the Gaussian surface is inside the charge cell, so it does not enclose any charge, so charge enclosed is 0. So flux is equal to 0 by epsilon naught. So when you put the value for flux, that is ei 4 pi r square, then you will get ei is equal to 0. So there is no electric field inside the charged cell. So we have found electric field outside the sphere, on the surface of the sphere, and this is the electric field inside the sphere. So now we will draw electric field versus distance graph for spherical cell. So inside the electric field was 0, and on the surface it was k q by r square, which was maximum, and outside it was k q by r square. So it is inversely proportional to r square. That means if you increase the distance r, then electric field will decrease. So this is the graph. So for first case, inside, when the value of small r, that is distance, is less than the radius, electric field was 0. So out here you can see this side is electric field, this side is distance r. So till the surface there is no electric field. So on the surface electric field, when this r is equal to radius of the sphere, that time electric field was k q by r square. That time it was maximum. Now after that it is inversely proportional to 1 by r square. That means when r increases, E should decrease. So this is the graph for 1 by r square. So the electric field should decrease. So first there is no electric field, maximum electric field on the surface, then it decreases like this. So this is the graph for E versus R for the spherical cell. From the diagram also, so out here you can see when this R is less than this R, electric field is 0. On the surface, when this R and this R is equal, then electric field is kq by capital R square. So outside the electric field is kq by small r square. So this is the electric field due to a charged sphere.